So welcome. In this video, I want to do a sample problem working with integrated rate laws. So their given problem here is that we have this reaction of cyclopropane rearranging to form pentene, right? So we're given the reaction, and we're told the reaction is first order in cyclopropane. The measured rate constant is 3.36 times 10 to the negative fifth seconds to the minus 1 at 720 degrees Celsius. If the initial concentration is 0.0445 molar, what is the concentration after 235 minutes? Okay, so the first thing is to recognize this as a problem that's going to involve using integrated rate laws. Now, the purpose of using integrated rate laws in a large number of problems, right, is to look at the dependence of concentration over time. So a very common problem that we see is asking us to figure out, how much of a reactant is left after this amount of time, or how much is used up after this amount of time, or if the concentration changes from this to this, how much time did it take, right? These kinds of things, these kinds of problems that look at how concentration depends on time. Okay, so let's go for it. So the first thing is we need to choose the correct integrated rate law to use. Now, we were told in here that the reaction was first order in cyclopropane. Well, since there's only one reactant, that means the overall order is first order, so we're going to use the first order integrated rate law, right? So, again, don't have to memorize these equations, you just have to be able to recognize, the one that has natural logs, that's the first order integrated rate law. So we have our equation. Now, what do we know? Well, we're told what the initial, or the times zero concentration is, right? 0.0445 molar. We're told what the rate constant is, K, and we're told how much time has passed, 235 minutes. Okay. What are we trying to find? Well, remember, we're trying to find the concentration after 235 minutes. So we're trying to find the concentration at time t. So we know T, we know K, and we know the initial concentration. So we only got one variable that we don't know. Now, one thing that you have to pay attention to in some of these is you have to make sure your time is in seconds. So it's typically your rate constant is going to be given in seconds, so you need your time in seconds. But bottom line is the time units have to match. So if you know the rate constant in seconds, then your time has to be in seconds. So first thing is to convert 235 minutes into seconds. That's straightforward. 60 seconds per minute, 14,100 seconds. So at this point, we just plug in our numbers, right? So we have what we know, plug in our K, plug in our time, plug in our concentration at time zero, and then it's simplification, right? So we're going to do our multiplication. Notice the units here cancel. Seconds to the minus 1. Seconds, they cancel. We have plus. We take the natural log of this. The units don't change, right? This is a molarity, so our units are still molarity here. So notice this is a negative number. So we have, don't forget the minus sign here. So we have minus 0.047376 plus a minus 3.1123 molar. We get a minus 3.56861 molar. Now, I'm keeping extra significant figures here because I don't want to round to. Ultimately, I'm going to keep 3 significant figures because that's what my initial concentration is given in. So again, now we have to think about a little bit mathematically. How do I figure out what's inside this natural log? I need this concentration. So we need to do what's called an anti-log or an inverse log. So the inverse of a natural log is an exponential. So if I take the exponential of a natural log, they essentially cancel out, and I'm given back whatever I was taking the natural log of. So in this case, the concentration of cyclopropane. And here I just do e to the x, so e to the negative 3.5861. Solve that, you get 0.0277. Again, our units are molar. So now you've shown that after 235 minutes, the concentration has dropped from 0.0445 molar to 0.0277 molar. All right, so this is a basic type problem looking at integrated rate laws, the dependence of concentration on time. Now, of course, there are other things that you could also be asked to do. You could be given data and asked to find K. You could be given data and asked to find time, right? The idea is that you're going to be given all but one of the variables, right? But the key is to look for things where you're changing the concentration, from one to the other, and you want to know some effect. Right, so integrated rate laws, time dependency of concentration.